We are starting this deep dive today with probably one of the most famous phrases in physics, but also one of the weirdest, spooky action at a distance.
Right, spooky action. It definitely sounds like something out of science fiction.
Mhm.
And Einstein himself coined it, actually, because he really didn't trust the idea behind it.
But it's not just theory anymore, is it?
Not at all. We're diving into quantum entanglement, and it's very real
Yeah.
and looks poised to fundamentally reshape, the global internet, cloud computing, maybe even where all your data actually lives.
Okay, so our source material for this deep dive is mainly focused on that practical side, right? A draft paper by Rob looking at how entanglement could seriously transform global data centers.
Yeah, potentially leading to this massive centralization worldwide. That's the core idea we're exploring.
So that's our mission today. Figure out what this spooky action really is, look at the experiments proving it's feasible, and then what's the big so what? What does it mean for the cloud, which, let's face it, we all use constantly?
Exactly. It affects pretty much everyone who touches a connected device.
All right, let's unpack it. Foundational question first. What is quantum entanglement? Can we get a working definition?
Okay, at its heart, entanglement is this fundamental quantum thing where two or more particles get linked up, intrinsically connected.
Regardless of how far apart they are.
That's the key, no matter the distance. The quantum state of one particle basically can't be described without describing the other. They act like a single system, even separated by miles, or potentially light years.
That's the non-local correlation part.
Precisely. Non-local correlation. It means they are connected beyond classical locality.
I think the immediate jump people make is thinking, faster than light communication, breaking the cosmic speed limit. That's why Einstein found it spooky, I guess.
That's the natural thought, yeah. And it's crucial we clarify this bit. The correlation, the link between them, is instantaneous. But entanglement itself cannot be used to send, like, a regular message faster than light. No FTL texting.
Wait, hang on. If measuring one instantly affects the other, why can't I use that? If I measure my particle here as up and I know yours instantly becomes down, isn't that a signal?
But here's the quantum kicker. You can't choose for your particle to be up. When you measure it, the outcome is fundamentally random based on quantum probabilities.
Okay.
So you measure it, you get up, you instantly know the other one is down. But that up result was random chance. To make sense of it as a 1 or a 0 in a message, the person measuring the other particle needs a key or some comparison info.
And that key has to be sent normally?
Exactly. Sent via a classical channel like radio waves or fiber optics, which is limited by the speed of light. So the correlation is instant, but usable information transfer still obeys Einstein.
Okay, that distinction is critical. Instant correlation, but not instant messaging. So if we can't send messages FTL, what's the actual practical use of this instant link?
The use comes from that certainty the link provides. The source example uses photon polarization. Entangle two photons. Measure one, find its polarization is vertical. You instantly know with 100% certainty its partner is horizontal, even kilometers away,
Without needing to check the other one.
without needing to wait for any signal traveling between them. That immediate knowledge, that guaranteed correlation, is what might let us bypass certain classical delays for specific quantum computations. It really messes with our classical ideas of cause and effect needing to travel,
That makes sense. The challenge isn't breaking physics, but cleverly using the instant quantum connection for tasks where waiting for a classical confirmation signal is the bottleneck.
You got it. And the fact this spooky connection is real is why there was so much effort to test it rigorously.
Right, and this is where it gets really exciting for practical applications. This isn't just math on a blackboard anymore. It's tested, proven technology. What were the key experiments that really cemented entanglement as something, well, network ready?
It kind of happened in stages. Stage one was nailing down the physics, proving it wasn't some misunderstanding. That breakthrough came around 2015 with the Bell test experiments.
Bell tests?
Yeah, multiple teams. Henson, Justina, Shalm, among others, conducted what are called loophole-free Bell tests.
Loophole-free, what does that mean here?
It means they systematically closed off any possibility that the results could be explained by normal classical physics, maybe involving hidden information we just didn't know about.
The local hidden variables idea, like the particles secretly agreed on their states beforehand.
Exactly. For decades, people wondered if there was some hidden instruction set. These tests, using entangled photons and electron spins over kilometer distances, slammed that door shut. They proved the correlations were truly quantum, truly spooky. That confirmed the physics.
Okay, physics confirmed. Stage 2, then, must be about getting it to work in the real world, in our existing networks.
Precisely. That big step came in 2024 from Northwestern University. They demonstrated quantum teleportation, transferring a quantum state, not the particle itself, over about 30 kilometers of active fiber optic cable.
Active fiber.
Unique fiber that was also carrying normal internet traffic at the same time. That was huge. It showed that these incredibly delicate quantum states can survive and function within the noisy, busy infrastructure we already use.
Teleporting quantum states alongside Netflix streams. Okay, that's a massive engineering proof point for scalability.
Absolutely. And that leads to stage 3, looking towards maybe 2025 applications, using it for actual computation between separated points. Researchers at Oxford demonstrated modular quantum computing.
What did they do?
They performed a fundamental computing operation, a logic gate, between two quantum processors, physically separate trapped ion systems linked only by quantum teleportation.
So, not wired together classically, but computationally connected through entanglement.
Correct. It proves the concept of distributed quantum computing, where different quantum modules can work together over a network.
Okay, so we've gone from, is this real, to can it work in our cables, to can it link processors for computation? Seems like yes on all counts. But 30 kilometers is a long way from a global network connecting continents. What are the big hurdles to scaling this up?
Oh, the hurdles are substantial. That's why we don't have a quantum internet lighting up the globe just yet. The two main ones are probably qubit coherence times, how long the quantum state lasts, and just massive photonic losses over long distances.
Let's take coherence first. What is coherence time and why is it so short?
Think of a qubit, the quantum bit, as being in this super fragile superposition state. It holds quantum information. Coherence time is just the tiny window, could be milliseconds, even microseconds in a noisy network before things like heat, vibration, or stray fields mess it up.
It decoheres, collapses back into a normal bit.
Basically, yes. The quantum magic disappears. The entanglement link literally just falls apart if you try to stretch it too far or wait too long.
Okay, so if the link keeps dying, how on earth do you bridge an ocean? You can't just send one photon from London to New York and hope it arrives entangled, right?
Right, that won't work. The solution borrows from classical networking, quantum repeaters, and entanglement swapping.
How does that work?
Instead of one impossibly long entangled link, you create a chain of shorter, more manageable entangled segments. Let's say London to a ship in the Atlantic, ship to another ship, ship to New York.
Okay.
Then, at the connection points to ships, in this example, quantum repeaters perform an operation called entanglement swapping. They essentially stitch the entanglement together, connecting the endpoints, London and New York, without ever having needed a direct link between them.
That sounds incredibly fiddly, keeping all those short links synchronized and swapping entanglement perfectly across thousands of miles.
It is incredibly fiddly. Massive engineering challenge. And it requires specialized hardware. The source material mentions companies developing dynamic modular quantum network units, or QNUs.
Like hardware boxes.
Yeah, think rack-mounted units, like stuff from New Quantum mentioned in the paper. These boxes integrate the photon sources for entanglement, the detectors, and crucially, the very fast, low-latency control systems needed to manage this whole repeater chain and distribute entanglement reliably, potentially to many users, in a data center context.
Okay, so the hardware is being built to tackle the repeater challenge. This brings us back to the big picture, the so what. If we can eventually span continents with these quantum links, why does that revolutionize data centers? Why do we have so many data centers dotted around the world right now anyway?
It really comes down to one thing: the speed of light limit in classical communication, latency, round-trip time.
The delay it takes for your request to get to a server and the answer to come back.
Exactly. Today, companies build data centers close to users in major cities worldwide because that physical proximity minimizes delay. If a server is thousands of miles away, even at light speed, there's an unavoidable delay of tens of milliseconds.
And for some applications, that's too slow.
For things like financial trading, real-time gaming, controlling remote robotics, industrial automation, those milliseconds are critical. So they spend vast amounts of money building and maintaining lots of local compute power everywhere.
Okay, so physical distance dictates costly decentralization today. But if entanglement allows certain operations to happen without that round-trip delay,
then the need for that physical proximity might evaporate, at least for those specific tasks. That's the potential paradigm shift. If you can achieve reliable, deterministic, remote quantum operations, manipulating or reading a quantum state instantly via entanglement, without waiting for a classical confirmation signal to travel back and forth.
You bypass the light speed limit for that part of the process?
Correct. For certain latency-critical subroutines, the quantum link could provide the answer or perform the action effectively instantly, regardless of distance.
So what does the global cloud infrastructure look like in that world?
Well, instead of hundreds of regional data centers all running heavy compute loads, the model could flip. You might have just a handful of massive centralized quantum cores.
Mega data centers.
Yeah, huge facilities housing these quantum classical hybrid supercomputers. Everywhere else, they just run thin clients, relatively simple local machines that rely on the instant quantum connection to the central core for the really demanding latency-sensitive stuff.
Wow. So going from, say, hundreds of major data centers down to maybe 5, 10
Yeah,
globally.
something like that. It's a radical centralization. The potential benefits are enormous. Think about operations costs, control.
It sounds like a massive simplification. You cut down on redundant real estate, power, cooling, managing all those distributed sites.
Absolutely. The cost savings could be astronomical. And managing a unified global system from a few central points is vastly simpler than coordinating hundreds.
But hang on, concentrating all that global compute power, especially quantum computers, which need serious cooling, wouldn't those few megacenters be insanely complex and power-hungry? Like, physically challenging to even build and run?
That's a very fair point, and definitely a huge engineering challenge. The underlying assumption, perhaps, is that the computational efficiency of quantum systems for specific tasks solving certain problems exponentially faster might mean the overall resource footprint, while concentrated, might not be impossibly larger.
Or maybe the operational simplicity of managing just 5 sites outweighs the complexity within each site.
That's likely part of the thinking. Dealing with the logistics of 5 incredibly complex cooling systems is probably still preferable to managing the cooling, power, and security for hundreds of distributed, less complex sites all over the world. You concentrate the hard problems.
Still, there has to be a catch. We said this is still aspirational. What's the big if?
The biggest if, the thing holding this whole revolution back, is achieving that deterministic remote state control. Getting the entanglement link to perform the desired operation instantly, reliably, every single time, without needing that classical feedback loop first.
So it's not enough for entanglement to just correlate randomly. It needs to be precisely controlled at a distance.
Exactly. We need reliable remote manipulation and readout via the quantum link alone. Progress on things like qubit coherence and repeater protocols is steady, but getting that perfect, instant, reliable control across global distances, that's still very much at the cutting edge of physics and engineering. The concept is solid, but the execution requires near perfection.
Okay, that's quite a journey we just covered. From Einstein being puzzled by spooky action at a distance, all the way to a potential future where global computing power is consolidated into a few quantum-powered megahubs.
And all driven by using this weird non-local correlation to effectively sidestep the speed of light delay for critical operations.
It really hinges on that deterministic control, doesn't it? Making the spooky action reliable and useful without waiting for classical signals.
Absolutely. Maintaining that perfect, immediate quantum connection across continents, the stability required is just immense, beyond what we can routinely achieve today.
Which leads to a final thought, maybe for you, the listener, to chew on. If, and it's still an if, but if engineers manage this, if entanglement allows us to collapse global data infrastructure down to a few points by overcoming distance for computing, what other field might be next?
Right. What other area of human activity is currently limited primarily by the speed of light or the friction of physical distance? That could be totally transformed if we could overcome locality.
Something to think about while we wait for the quantum internet to arrive.
Definitely something to mull over.
That's all the time we have for this deep dive.